In this video lecture, I want to talk about a method for solving differential equations called separation of variables. So I have this differential equation here, y prime equals 2x over y. So if we just remember what it means for a function to be a solution to a differential equation, it means that we're trying to find a function y, or y equals f of x, such that if I take the derivative of that function, it's the same as taking 2x and dividing by the function. So the first thing we're going to do for this idea of separation of variables is just to rewrite y prime as dy dx, which is just different notation for the same thing, for the derivative, right? And the reason for that is for separation of variables, I want to basically have a dy term on one side and a dx term on the other. So I could multiply both sides by dx and multiply both sides by y, and that's going to give me y dy equals 2x dx. All right, so that now we basically have separated the variables in the sense that my y and my dy are on one side, and my x terms and my dx are on the other side. And so at this point, what I'm going to do is I'm going to integrate both sides. So I integrate this side with respect to y and this side with respect to x. So I end up with y squared over 2 plus c equals x squared plus c. But these aren't necessarily the same c's, so I'm going to call this one c1 and call this one c2. All right. Now what I want to do is I'm just going to basically get all of my variables on one side and get my c's on the other side. And I'll also multiply through by 2 just to get rid of the y squared over 2. So if I do that, so if we multiply through by 2 and bring the x squared term over, I end up with y squared minus 2x squared equals, and I also, the c's got multiplied by 2, so I have 2 times c2 minus c1. All right, so that's just the algebra. And here's what I want to point out, because this is just in general what you'll see with the notation here. c2 is any number, c1 is any number, but they're not necessarily the same number, and then I'm multiplying them by 2. But this whole thing, let's just call it c, because if I take any number, subtract some other number that's arbitrary, and multiply it by 2, I can just call that, just simply, this is more just kind of a simplicity of notation, rather than having something that looks like this. Let's just call the whole thing c, since that's really what it represents. It just represents some number. And then, of course, on this side, it just stays the same way. So I have y squared minus 2x squared equals c. So I know sometimes this can be a little confusing for students, but again, it's really just to simplify it. It's not wrong to have this. It's just simpler to kind of represent the whole thing with some arbitrary constant that we call c. Now, let's just verify that what we found actually is a solution to this differential equation. All right, so if you take the derivative of y squared using implicit differentiation, that's 2y dy dx, and then minus the derivative of 2x squared, so that's minus 4x, equals, and we know the derivative of a constant is 0. All right, so let's try to rearrange this and solve for dy dx, which we said is the same thing as y prime. So I get dy dx equals, and I bring the 4x over, and then divide by 2y, which is the same thing as 2x over y, and that's what I started with. So this is a solution to the differential equation. The other thing I want to point out here is that we're not always going to be able to explicitly solve for y as a function of x. We might end up with something that's not a function, like this is not a function. So don't worry about having something in terms of y equals when you're trying to solve the differential equation using this method. Okay, so this is the general idea of the method. Let's get all the y's and dy's on one side, all the x's and dx's on the other side, and then we integrate each side. So let's look at another example. All right, how about, make sure we're centered here, y prime equals y over x squared. So again, first thing I'm going to do is rewrite this as dy dx equals y over x squared. So if I multiply through by x, or dx, to get it over on this side, and then divide through by y, I end up with dy over y equals dx over x squared. And it might be easier to see that as just 1 over y dy equals 1 over x squared dx. So now we're to the point where we can integrate, because we have the y terms and the dy on one side, the x term and the dx on the other side. So we will integrate. All right, now we know the antiderivative of 1 over y is the natural log of the absolute value of y. And again, we'll call this maybe plus c1 equals, and over here we're going to get negative 1 over x plus c2. All right, I mean, I'm assuming we know how to go from here to here. You could just write this as x to the negative 2, add 1 to the exponent, divide by the new exponent. This is what you'll get. All right, so let's try to simplify this a little bit. If I bring the c1 over, I can rewrite this as ln of absolute value of y equals negative 1 over x plus c2 minus c1, and I can take this whole thing and call it c. And now what I'm going to do is, just to make this a little bit easier, I am going to raise both sides. I'm going to make each side the exponent of e, because this, e to the natural log of y, gives me y. All right, and this is going to give me e to the negative 1 over x plus c. All right, now I just want, using the properties of exponents, that's the same as e to the negative 1 over x times e to the c, right? Because if the bases are the same and we multiply, then we can add the exponents. So we're just going the other direction now and separating them. And again, the same idea that, we have c2 minus c1 is just some constant that we can call c. Well, e to the c, so maybe we should call this c3, because I can just call e to some constant. I can just call that c. So finally, we would end up with y equals c. We usually put the constant in front. C e to the negative 1 over x. All right. So this again is our general solution to this differential equation. All right. Once again, let's just quickly verify that what we found is indeed the general solution. So if I take the derivative, I get y prime equals, the constant just stays up front. That's what it does when we do derivatives. And I multiply by the derivative of the exponent for e to the negative 1 over x, which is 1 over x squared, e to the negative 1 over x. All right. Well, let's rewrite this. I'm just going to switch these two, and you'll see why in a moment. I'll have c e to the negative 1 over x times 1 over x squared. But what is c e to the negative 1 over x? Well, that's y. That's what we have right here. So this equals y times 1 over x squared, or y over x squared. That is what we started with. So this is indeed, if I take the derivative, I get y over x squared. So this is a solution to that differential equation. Okay, so maybe the thing that was a little bit different here is if I end up with a natural log, we like to solve for y. I know I said here it's not possible to solve for y, but when we can solve for y, it is nice to have something of this form, in terms of a function. The other thing that was a little bit different here is that when we end up with this constant here, this e to the c, we're just going to call that c and we'll bring it out front. Okay, one last example of how to use separation of variables to solve a differential equation. So let's look at this differential equation. This one's a little bit more complicated. X times y dx equals plus e to the negative x squared times y squared minus 1 dy equals 0. And what we want to find is the particular solution that satisfies y of 0 equals 1, which another way to think of this is here's my x value, there's my y value, right? So another way to think of it is it passes through the point 0, 1. So we first need to get the general solution, and then we can use this to find a particular solution. So the first thing I'm going to do here, again, separation of variables, I have this dx term and I have a dy term. Let's get them on opposite sides, right? So I'll have xy dx equals negative e to the negative x squared, y squared minus 1 dy. And again, I want to get this y over here, so I'll have to divide it, and I want to get this over here. So if I multiply by negative e to the x squared, then this whole thing will become 1. So I end up with x times, and I'm saying times negative e to the positive x squared. So I'm going to bring the negative up front, e to the x squared dx. All right, because if I multiply negative e to the x squared times this, I get 1, which is what I want. And then I'm going to divide by y to get that over. So I get y squared minus 1 over y. So again, at this point, it's really algebra. We're just rearranging our equation using algebra. Whoops, so that's supposed to be a dx. That's why I'm doing this whole thing, is to get all my x's and dx's on one side, and then I get all my y's and dy's on the other side. Hence the name, separation of variables. All right, so now what I need to do is integrate. All right, so the integration here is a little bit more complex than what we've done in the previous examples. But this isn't too bad. Notice that the derivative of x squared is 2x, which is just off by a factor of 2 from x. So we could let u equal x squared, du equals 2x dx. So I divide by 2, 1/2 du equals x dx. So on this side I'm going to have, and I bring that negative out, negative 1/2 integral of e to the u du. On this side, what I'm going to do is I'm going to rewrite that as y squared over y minus 1 over y. Right? This is this idea of a common denominator in reverse. Separate it. So this equals, so I'm integrating, y squared divided by y, that's y, minus 1 over y, and I'm integrating that whole thing. So I can integrate that term by term. So that's going to give me integral of y is y squared over 2, integral of 1 over y, antiderivative is natural log of y, and I'm going to have this c1 factor here. Here, I'm going to end up with negative 1/2 e to the u, we'll call that c2, which is, we said u is x squared, so negative 1/2 e to the x squared plus c2 equals y squared over 2 minus natural log of absolute value of y plus c1. All right, now all I'm going to do is clean this up a little bit. So what I want to do is, just to make it look better, easier to look at, I'm going to multiply both sides by 2. So this is what we're focused on right now, right? We got this from doing this integral, we got this from doing this integral. So we got that here, this came here, and if we multiply by 2, we can get rid of these factors of 2, makes it a little bit easier to look at, and we'll combine our c's on one side. So I would get, multiply this by 2, I would get negative e to the x squared plus 2c2 equals y squared minus 2 ln absolute value of y plus 2 c1. All right. What I'm going to do is I'm going to take the constants and I'll put them all over on this side. I'm going to bring over my x squared. So I end up with c equals y squared minus 2 ln of y plus e to the x squared. All right, so that is, I claim, the solution to this differential equation. So a little bit more complex, getting things separated here, and the integrals were a little bit more complex as well, but I don't want to do all easy examples because then when you got to try to do something a little bit more difficult, you might get stuck. So, so this is we could verify that this is the solution to this differential. Oh, I have one more thing to do, don't I? I want to solve for C. Let's do that first. I was going to say I'm not going to verify that this is a solution to the differential equation because that will take as long as solving the differential equation did. I think it was worthwhile in the first two examples to do that so that we could see, yes, indeed, this is getting us to the solution to the differential equation. But we do need to do this piece right here. So let's go back. We know that x is going to equal 0, y is going to equal 1. So I have c equals 1 squared minus 2 natural log, I don't need the absolute value, it's natural log of 1, plus e to the 0 squared. All right. Well, 1 squared is 1. Natural log of 1 is 0, so this whole term is 0, and e to the 0 is 1. So 1 plus 1, that equals 2. All right, that'll be the easiest math we do today. All right, so what I end up with then finally is, so this is my general solution. So my particular solution will look like 2 equals y squared minus 2 ln absolute value of y plus e to the x squared. All right, so that's separation of variables to solve differential equations.